Hey there hackers! In this video we will look at the Day 19 challenge in Advent of Code. As we are approaching the end of December, the problems are getting more difficult, often they require advanced techniques such as dynamic programming. Brute force solutions are less likely to work. I managed to solve this one in Uiua using pattern matching and recursion, even though I must warn that this is a rather slow and inefficient solution. Both of these methods are not really part of the core array programming techniques, but they can be pretty powerful and they offer a different approach to implementing control flow. Oh, and we will also talk a bit about performance improvement through memoization and multithreading. Brief overview of the challenge itself. According to the backstory, we need to combine towel patterns made up from different color stripes to make more complex designs. The input has two sets of data. The first one is the list of the patterns, and the other section contains the possible designs we need to create. Each letter means a different color. Actually, some designs are impossible to create from the given patterns, and in the first part we need to figure out how many are possible. In the second part, we even need to count how many different ways those designs can be built. Processing the data is a little more challenging than usually because we have two sections with different structure. In Viva, it causes us more pain that each pattern and each design has a different size, so we cannot store them in a normal array, we are forced to box them. But it's not so tragic. First, to separate the two sections, we can use a pattern matching trick. Unstring with two endline characters will split the input across the empty line. The underscores are placeholders for any character. Now we can observe that we only need to capture the letter groups from both sections. All the other characters, the new line, the space and the comma, are positioned lower on the ASCII chart than the letter A. So we can put a mask on any character that is greater than or equal to A, and then partition using the box function. This way, different size strings can be collected to the same array. And we can enclose this operation in a both modifier so that it is applied to each section simultaneously. Let's bind each array to a name, and we can display them with some labels for our convenience. Remember, the task is to build up each design from a sequence of the patterns, and we can reuse any pattern any number of times. Viva has many different search functions that could be applied here, but I went with pattern matching because it's quite interesting. There's a long page about it in the Viva documentation. I will only highlight the prefix match here, which will help us with this task. It works with numbers and characters too. Unjoin can be used to match a specific prefix in another array. For example, we can check if the word hello starts with hell, and we get back the rest of the characters, in this case a single O. When the full pattern matches, an empty string is returned, and in case of no match, an error is raised. We can catch the error and substitute a different value with the try modifier. Well, this looks really interesting, but we want to test not just a single pattern, but with many different patterns that we want to apply dynamically, based on the task input. Using unjoin without the parentheses is actually doing something else. It consumes only one argument and takes it apart to first and rest of characters. But luckily, the anti-modifier comes to our rescue. It is very similar to un, but in case of dyadic functions such as join, it leads to a different inverse behavior. So we can match a dynamic pattern with anti-join. After this much preparation, we are now well equipped to tackle this AOC challenge. Let's focus on the first design, while we build up the solution logic. We can check if anti-join works on the first pattern, which is expected to not match. The first obstacle is to penetrate the box boundaries, using the content modifier. Now to handle the matching error, we can use try and put a guard value that we can distinguish from any actual result. There is no null in Uiua, and the empty string wouldn't work for this purpose because that is actually the favorable outcome when the matching is fully completed. We can also check that it works correctly with the last pattern, leaving us with the remaining characters. Now to validate all the pattern prefixes against a single design, we can use the row modifier to loop. The only catch is that the results can again have variable lengths and they can only be stored in a boxed array. The easy fix is using the inventory modifier directly after rows instead of the content modifier. This will box any result from the loop, including the non-match cases. Now one more thing is to remove the guard value from the result. Again, we need to pay attention to how we loop and compare boxed data. Well, if I put the guard character in a box, the rows modifier will be able to combine it with each item in the match results, and the not equal operator can compare them correctly. Then filter the results with keep by. Now this line will work nicely as a separate function, taking one piece of the design and returning all the remaining parts when any pattern can match the beginning. I call it towel, because it's chipping away one towel at a time. The key part of the solution is building a recursive function. Now we can do this quite easily in Viva. The only syntactic requirement is that we must specify the function signature, how many values the function consumes. Then we can refer to the name inside the function body, what we used in the binding. There is just one caveat to using recursion. When the data is too complex, then we can hit the recursion limit, particularly in the online pad. But with the test data, we will be safe. We want to write a function which takes a section of the design and returns the number of ways it can be constructed. The task doesn't require us to mark which patterns were used. In any case, the argument of the function will be a box string, either empty or not empty. Let's start with constructing the base case or the exit condition. After copying the argument, we can use content match empty string to make sure boxed values are compared appropriately. Then a switch function follows, and when the input is empty string, we return 1 as the result, discarding the empty string with the gap modifier. In case of no match, we have to process the input further with the towel function. Really, the only thing left is that each result of towel will need to be evaluated by the weave function again. And in the end, add all the numbers. This will tell us how many times the empty string was reached through prefix matching. For the first design, the result 2 is correct. Let's check also for all elements of the sample. 6 of the designs return a positive number, and 2 of them 0. For the first part, we only care how many possibles are in the sample, so we can normalize the whole array to 1s and 0s using the sign function, and then add all the 1s to get the result of part 1. For part 2, we actually have to delete the sign character here, and we get a total possible ways to construct all the designs. To be honest, this runs fast on the test data, but it will perform much worse on the real data. For one thing, in the online pad it will fail because of the recursion limit. But if you try on locally installed Uiua, there are 2 things you can do to optimize a little bit. First, we can memorize the weave function so that every function execution is automatically cached and previously used values don't need to be tried again. In case of running the calculation for each design, we can process the data in multiple threads. For this, we only have to write pool inside the row modifier and collect all the spawned threads with weight. So Viva will be able to take advantage of multiple CPUs and run some of the cases in parallel. With these improvements, the result on my machine was calculated in about half a minute. Dynamic programming is a very deep rabbit hole, and I'm not really an expert either. The point is generally that we need to figure out a way to reduce the task to smaller and smaller subproblems, which ultimately becomes trivial to solve. But sadly, there is no magic formula or universal Viva glyph here, because every algorithm is completely unique and tailored to the specific problem. So I guess the only way to invent this type of solutions is by developing an intuition to DP through solving lots and lots of such problems. It's a bit of a catch-22 situation. Anyway, the recursive solution that I was showing so far is also something like this, but it comes with a lot of computational overhead because all the recursive function calls need to be kept in memory. But usually there is an iterative or even better array-based alternative that comes with vastly superior performance. I would like to showcase one such example that was created by a fellow Vivan with the nickname BKDJ and shared on the Viva Discord server. It's the first time that I am presenting someone else's code. Honestly, I would not be able to explain it step by step, I only vaguely understand the gist of it. Well, this piece is objectively a beauty to behold. It even has a test module that verifies the correctness based on the sample data. But the point is the first 3 lines. The data function does the parsing, same way that I presented. And we can recognize the solution loop, and the difference between part 1 and part 2 is also familiar. The logic that happens in the ways function is more difficult to understand. The function takes also a single design and all the patterns. The author gave me a heavily annotated version of this code that also shows the stack trace in the output, so I will share the link if you want to study. This solution is based on the find function, which is able to search for every occurrence of each pattern in the design and mark the letter locations. Then there is a fold that processes this matrix and calculates the number of ways to build a design from all the patterns. I just want to highlight that several others shared similar solutions on the Discord channel, and I encourage everyone to study other people's codes because they are a tremendous source of learning. By the way, this solution does run in the online pad on the full data without limitations, and takes only a couple of seconds to finish, so indeed the performance is much better than the recursive one. When it comes to language capabilities, pattern matching and recursion are just additional tools which complement the powerful array features of Viva. The way how pattern matching works is quite unique, and it opens up some exciting possibilities to formulate our code. We can use it to avoid resorting to regular expressions, and we can also validate or extract some part of an array with this feature. Recursion is not really encouraged in Viva, but for fans of functional programming and particularly for problems that are less sensitive to performance issues, it's often a great way to express certain algorithms more naturally. We have also seen some options to improve performance with memoization and multithreading. All things considered, Viva is quite capable to solve even some of the most difficult AOC challenges out there. Thank you for watching this video, keep coming back for more if you found it interesting. See you around!